One of the interesting implementations of using the maze generator algorithm resides in taking images or some systems that deviate a little bit from the original scheme of two-dimensional arrays in order to generate some more interesting patterns. Let's see how we can accomplish that. Here I have two images that I'm going to be using for this tutorial. We're going to be using the CV2 library, OpenCV, which we have already talked about a little bit. I'm going to start a new project in this folder that I'm simply going to call main.py. The general idea of this algorithm is to implement the maze generator that we saw in previous tutorials and sort of concatenate its functionality with a series of helper functions that will read an image, resize it, and then transform it into a two-dimensional grid of values. Remember the attributes of a tile. It has a position in the columns and the rows of that grid, a position in X and Y, and then the attributes that make it special for the maze generator are whether or not it has been visited and the information regarding the walls. Let's start first by loading the image using OpenCV. We're going to divide the program in three different sections called the modules, the data definitions, and the code. In the module section, we're going to import OpenCV and also the OS library. In the data definitions, we need to set a couple of constant parameters representing the information on where we can find this image. The first one will be the path of the image. And that path will simply be the current position where this file is located, followed by one of the images of interest. I'm going to pick reference 2, which is the image of the words maze, because I liked it most when running the algorithm. The next element will be to load the image. To load the image, let's first create a data definition image that is going to be called img. And this is going to be a NumPy array. The NumPy library represents a set of tools that allows us to traverse two-dimensional or n-dimensional matrices with ease in a way that is more efficient than what Python normally does with arrays. The interpretation here is a collection of arrays, of numerical arrays. It turns out that a NumPy array is a collection of floats most of the time that forms an image. And therefore its dimension should specify a width and a height. So let's see how we can load this. We say img equals to cv2.imread. And we're going to specify the path where we want to read it. And we're going to specify the parameter 0, which represents grayscale. If I print the image right now, what I'm going to get, hopefully, if my environment figured out the right place to look for the kernel, it did not, so I'm just going to run it directly as a Python file. Because at the bottom right corner, I can see the name of my environment, and it does say pygame environment, and I know that I installed OpenCV in there with Anaconda. Here we have the results of our program. And as you can see, we have pretty much a matrix of zeros. And the reason why we have a matrix of zeros is because we are looking at the very top left corner of this array and at the very bottom right corner. And you can see that they're all black pixels. NumPy has a series of really interesting methods that allows us to gather information about the array that we are working with. In this case, we're going to print the NumPy array's shape. This information that you can see down here at the bottom is represented with a compound data type of type tuple with two elements. The element on the left represents the number of rows, which is flipped relative to the way that we are used to look at the number of columns and the number of rows. So this is the number of rows, and therefore this is the number of columns. So this image is 493 by 1024. If we want to make every single pixel its own tile, this maze is going to be really big. What we are going to do instead is to reduce the dimensionality of this matrix. We're going to recycle the name of this variable, and then we're going to use cv2.resize. Resize is a method from the OpenCV library that receives an original NumPy array, and then as a tuple, the information relative to the new values for the width and the height. Here I could specify any arbitrary dimensions that I'd like, and the matrix would get modified relative to those transformations. But in this case, the ratio by which the image is width versus height carries information. So instead, I'm going to set a couple of new parameters called W and H that will represent the information on the shape of this image. And this will look a lot like typing img.shape followed by the particular element in the tuple that I'm referring to. Notice here that I am using the same tuple twice. I would need it for the width and I would need it for the height, and this works fine. But there is a way to compress the declaration of the variables by deconstructing a tuple and putting every single value inside of their own variable names. It will look something like this. We have the height and we have the width, and that will be equal to the image.shape. The value h will receive the value 493 and the value w 1024. The idea here is to multiply those values by a certain percentage. Let's make it 10%, the original scale, and that is the set of values that we're going to specify here. In this case, we're going to set it to h and we're going to set it to w. Let's print the image.shape and let's see if our program works. So it seems that we cannot use this technique in here because the program requires to multiply numbers instead of tuples against numbers. So we're gonna set it as it was, h0, and w is img.shape at index 1. No problem. Let's run it again and let's see what happens. If we run this again, we get an error, and I believe that error has to do with the fact that we need to do some casting because the dimensions of a matrix have to be given as integers. And this time it works. We have the rescaled version of this image. The next thing we need to do is to define the class tile, something that we will do by going to the previous project and simply copying and pasting the data definition for the tile. We will look over it once more before we can implement the maze generation. Here we have the program from the previous implementation, the same code that we had in the tutorial for the maze generator. Here we have the class tile. The attributes in the class contained the number of the column and the rows, the position in X and Y given in the coordinates relative to the screen, then the color of the tile, and then the information that is unique for this particular maze generator, and that is the information on the walls. When the values given here in binary are 1, it means that the wall has to be drawn. The walls are arranged in 4 values, starting at the right direction and then following a clockwise direction from there, so that we have always the same standard views when going through the process of coding. The next element is whether or not we have visited this tile already, and at the beginning the default value is going to be set to false. This class has a set of methods that allows us to draw the tile by simply calling upon the draw sublibrary of the pygame library and also draw the walls, a process that has to be done separately. The process of drawing the walls represents 4 if statements, one for each of the walls, evaluating whether or not the particular index from the right to the up in a clockwise direction, following the index 0 to 3, has a value of true when casting the integer into a boolean. And if the answer is yes, then we map the points in which that particular coordinate or point that allows us to draw the line for that particular site is located, and then we draw the line. After that, we generate a tile row, which is the composite of multiple tiles, represented with a compound data type of type list given by the number of columns that each of the rows has to have. This process happened procedurally. We initiated an empty list that we populated using a for loop, and this process contains 2 steps that represent creating the tile and putting it in the tile row container. From there, we expanded to the dimensions of the grid, and notice that this is also a for loop. This process we already encountered, which is drawing all of the tiles inside of one row. And then we append it. That is the basic information in this program. So let's copy everything from the class tile down to the grid, including the template. I'm gonna go back to main and I'm gonna paste it in there. The general idea is to give a new attribute to our tiles, indicating whether or not this tile is a valid tile to run the maze generator or not. To do that, we are gonna add a new attribute that will be called valid. And this is gonna be an attribute that will be received directly from the constructor. Notice that we don't have a parameter called resolution, and we haven't set the dimensions either. So let's add those parameters. Dimensions will now be equal to the number of columns and the number of rows represented by this rescale image. In this case, img.shape at index 1, that's the number of columns, and img.shape at index 0, representing the columns. Then we can generate a screen. A screen will be generated by multiplying the elements inside of the constant dimensions, representing columns and rows, by the resolution. And that resolution for now is gonna be 8. Here we take dimensions at index 0 and multiply it by the resolution, and we do the same for the number of rows. After creating the screen, represented in pixels, we can finally create the screen by using the display sublibrary of the pygame library and using the method setMode. Here we can pass the screen. We need to also import the pygame library. Once everything is in place, let's play this and let's see if we get any errors. Okay, it seems that we don't have any errors. And also, in the brief moment that I can see the image, I can see that it's way taller than it is wider, which means that one of these numbers is flipped. And the reason is because resize takes first the columns and then the rows. If I run it once more, this time it has the right dimensions. Okay, we can proceed. Now that we have a tile, it's time to scroll down all the way down to the grid, which procedurally generates the entire two-dimensional array, which is the image. In this case, the grid will inherit its dimensions relative to the original constant dims, representing the number of rows and columns. The only parameter we need to change here is whether or not this is a valid tile. And we need to evaluate that particular pixel in the position R and C to determine if this is a black or white tile, therefore invalid or valid tile. So we're going to use an if statement here by asking a question. And the condition is whether or not the image at the index R and C is bigger than 127. My image is only black and white. There is really no value in between. But even if it did, I would probably end up producing something very similar to thresholding, which is exactly what this process does. It takes an original image in grayscale and then reduces, based on a particular value that we use as criterion, all of the pixels under that threshold into a black color and everything that is above that threshold into white color. So our code is implementing the equivalent here while deciding which of the tiles we're going to be drawing in the maze. If the answer to this question is yes, then we create a tile and we pass through. And otherwise we pass false. So how can we use the information regarding the validity of the tile to decide whether or not we can draw it during the algorithm? Let's print some information about the grid, like its length, and let's see if the information is in there. There seems to be a problem in line 65, and I believe, yes, it's because we created an example here of the tile and the definition of a tile has changed. So I'm just going to add novi value of false in there. There it is, so the program works. Let's see if we can visualize it. So let's start simple by going to the tile and then identifying the particular color of the tile relative to whether or not they are a valid tile. And to do this, we can go to the draw tile function, and before we call for the execution of drawing those pixels, we can call a helper function called self.getColor. GetColor will be deposited inside of that class, and its function is simply to return, based on a series of if statements, what color this tile should be. If the tile in question is valid, then we set self.color equal to white. Otherwise, we're gonna set it equal to black. Let's go to the coding section and let's produce the image. To do this, we need to first divide the program in two main functions. The first one is the draw function, which is in charge of rendering pixels, and the update function, which is in charge of updating the steps in our algorithm. Then we're gonna use an infinite loop to run the two processes forever unless the user manually asks to halt the execution of the program. And as we discussed earlier, there is a problem when we don't specify the user interaction because the window halts whenever we try to move it or click on it. So let's fix that right away. We're gonna say that for every event in the list of events of pygame, if the event that the user is accessing is quit by pressing the top right corner of the window and closing the window, we set pygame.quit, this time as a method. Let's focus on the draw function. The draw function involves three main steps. The first one is setting the background color of the display. Let's make it something really obvious. Our program should not show us any red if we render the tiles properly, because every pixel is covered by a piece of a tile. Then we can do anything that is special about our algorithm, and finally we call for a handshake with the other programming language, which is actually handling the screen, that is gonna be accessed using pygame.display.flip. Some people like to use also updating here. I'll leave it to your criterion. And now we can copy the template for the grid and simply paste it down here in line 104. I'm gonna get rid of the comments, then fix the indentations. And the task at hand here is to draw. So we're gonna set tile.draw, and we're gonna set it to draw tile, which is the name of the method we had specified before, I believe. Yes, it is. And we also need to get rid of one of the pieces of this template, this one right here. Okay, so let's run the program and let's see what we get. And there is a compressed, more pixelated version of our image. Perfect. This is gonna be the ground. This is gonna be the playground for the next step in the algorithm, which is maze generation. Remember what the maze generator does. It uses first an agent, sort of speak, that simply represents a particular position in the grid. Then we evaluate which neighbors that tile has at any given moment. We pick one of those if there is at least one, and we tear down the walls in between those. Then we make the new neighbor the agent, and then we repeat the process. But sometimes the program will get stuck, and when that happens, we use backtracking. So let's go to the previous program and steal the code. Here we have the current tile, and that is gonna be what I've been calling the agent, and we also have the stack. So I'm just gonna copy these elements, and I'm gonna paste them right here. We're still in the data definition. I'm gonna move the code section a little lower. What's next? In the draw function, we seem to be drawing the walls, and we also seem to be drawing the tiles in a separate step. So let's follow that. Protocol, and we're gonna paste here, draw walls. Let's see what happens. Okay, the program still works. We have a helper function called getNeighbor, and this one receives the position of the current tile and determines which neighbors are available around us. We definitely need that. Tear down walls. We also need that one. It receives the particular tile of interest at this particular stage and the chosen neighbor, and then it tears down the wall between. So we're going to copy this and we're going to paste it down here as well. The update function receives a global variable CT for the chosen tile, which we will modify and we define at the beginning in the data definitions. And for each of the tiles, it determines its color. This is something that in our new functionality we already included within the template for the class tile itself, so we don't need this part. And then this is the event handler for pygame. This is the same version that we have in the new program, and this is where the algorithm takes place. If we have at least one neighbor, choose one at random, otherwise apply the backtracking. And I'm gonna paste it right here. It seems that this program uses random, so I'm gonna go to the top of the program and I'm also gonna import the random library. Let's go back where we were, and here we are. So let's run this and let's see what happens. It says that CT has been referenced before assignment. Let's find CT, it's right there. And the problem is in line 176. Oh, and that is because, that is correct, I didn't paste the global reference to the variable CT. Let's run this once more. And look at that, we have the maze generator again. But the problem is that this maze generator is not restricted to only the pixels that are white, and that is going to be the next step, which is surprisingly easy to implement. I'm going to close this for now, and then I'm going to go to the part of the algorithm that is in charge of evaluating if this tile should be chosen as a valid neighbor. That happens right here. We have 4 cases, and to each of those cases, we need to add the same logical addition, whether or not this is a valid tile. We will need to ask if there is a neighbor in that direction, if it has not been visited, and if it is also a valid tile. So here we can copy these elements, which reference the particular neighbor that exists there. And then we can paste them right here. If it is a valid tile as well, then we can add it. If we run the program once more, the program halts. Nothing happens anymore. And that is because the original tile of interest is located at the top left corner, surrounded by invalid tiles. The current tile is an invalid tile itself. So we need to make sure that we place it somewhere within the boundaries of the white pixels. I'm going to keep this value here because it's not hurting anybody, and I'm simply going to get rid of it on the stack. We are going to copy these 2 lines, however, and then we're going to go down here to the part of the program that handles events. We're going to ask if the event is of type pygame.mouseButtonDown. If the button that we are clicking is the button 1, which is the left button of the mouse, then we're going to go through every single tile in our 2-dimensional grid, and we will evaluate if the mouse is clicking on that tile. If it is a valid tile, we're going to set that value to be the current tile. So let's copy the template for the grid. We're going to scroll up a little bit, and we're going to copy this element right here, and then we can paste it down below. We fix the indentations, get rid of the comments, something that is becoming more and more standard for us. And then here we can ask a question. If the tile rect component is colliding against a particular point, which is given by the position of the mouse in the pygame window, then we are gonna also ask if this is a valid tile. Otherwise, there is no point in doing it, although the algorithm wouldn't take care of that particular case either way. We can try it. Actually, let's try it without it so that you can see what I mean by it. And then let's set the current tile to be equal to the tile, and let's append it to the stack. This was the part of the code that I had copied before. Let's go to the top of the document and let's also modify its size a little bit. Let's change it to 16 so that I can have, oh, that is now too big. I don't want 16. I'm gonna break the rules of the exponential 2 in the dimensionality of matrices, and I'm gonna set it to 12 instead. And you can see it here. So if I click in one of the black tiles, it says that pygame.mouse. Oh, I get an error whenever I click, and it is because the name of the method to get the position of the mouse is getPosition, not get. And this time the program should run. If I click in one of the black tiles, nothing happens because the algorithm is already set to avoid doing anything whenever the current tile is surrounded by invalid tiles. But if I click in one of the white tiles, you can see that the algorithm works. That's great. But we also have the problem of the outlines in the black tiles. We don't want those. So I'm going to close it for a minute, and then in the part of the program within the class tile that determines whether or not we draw the lines, we are going to add an if statement. And the question is if this is a valid tile. If the answer is yes, then we draw the lines. If we run the program once more, we have our maze generator. The magic about this is that I can click anywhere and it will start the maze generator from there. I'm going to start by going to the top left corner, and I'm going to click in this. I'm going to click in the very first square. Finally, I'm going to change the color of the lines from red to black as well before I leave in here, because I'm not really a fan of the red outlines. In fact, some people may have some trouble looking at the red lines against the white background. So I'm going to run it now, and this time with the black outlines, the maze looks much nicer, at least in my opinion. And here I can go to the top left corner of the screen, and actually I can click anywhere inside of this maze generator, and then it will start producing the maze from there. I'm gonna pick this very first square at the bottom left corner, let's say. And then I can just leave the program running for a bit, and I can get back later to it. The entire process took around 5 or 6 minutes, and there is definitely steps that we can take to maximize productivity when it comes to generating these images. It turns out that the most expensive part of the process is actually rendering the image so that the user can see it. The process of going through the steps of the algorithm are not that time consuming at all. So something you can do is to simply let the program run in the background, and once it's done, once the stack doesn't have any elements inside anymore, then you can render the image. I hope this tutorial is useful for some of you that are wondering how to make these interesting patterns over customized shapes and figures, and I'm looking forward to hear what kind of ideas you may have to implement these algorithms with.